Okay, so now you're already a pro at finding derivatives. You're about to enter a whole new world, and that's called antiderivatives. And the deal with antiderivatives is this. If you can take a function, look at this friendly function, and take its derivative, well, then you should be able to do the opposite, which would be take its derivative and then, like a salmon, swim back upstream to the original function. So imagine it like this. You didn't know what was there, but you were given that. Can you figure it out? Well, sure you can. Here would be my thinking. I would say, okay, I see that this has an exponent of 1, so the function that gave birth to it must have an exponent of 2. Because when I take this derivative, the exponent's going to lower by 1. And then I just kind of reason out 2 times 3 would give me my 6. Just like over here, I'd have to kind of imagine that this is an x to the 0 power, which means I would have to have an x to the 1 power here. Now there's something a little bit weird here. What's the derivative of a 7? It's a 0. So you kind of have a plus 0 here. Well, that's going to become a little pesky as we go on down this video, because that could be a 17, it could be a -8, it could be a 312. Any number, or constant as they say, will have a derivative of 0. So you really could have something else there and still be correct. Alright, so that usually is a little confusing until you start doing it in practice. So as I reveal these problems, it's probably smart for you to pause the video and see if you can swim back upstream from derivative to function. So here's the next one. Pause it if you want, and I'm going to go ahead and explain my thinking. Now that I have to swim back upstream and do the antiderivative, I see that's an x to the 2nd, so an x to the 3rd would be necessary. I would need a coefficient of 2. Now, every time I do an antiderivative, I stop for a second and I pause. I actually wipe my brain clean. I wipe my hand right across my forehead so my brain is wiped clean. And then I say, if this was a fresh derivative problem, what's the derivative of 2x to the 3rd? 6x squared. By wiping my brain clean and taking the derivative, I know I got that correct. All right, let's see, I would need an x squared, and then I would need a -6, and then a 1/2 x to the 1st power. And then technically, I could have any following number. So we're going to call that a plus c, and you have to include that, or you will probably end up losing a pesky point. This plus c represents the fact that it could be 17 or pi or e or -4. Its derivative would be 0, which you see there. Okay, so these first two are examples of reverse power rule, which just takes a little bit of disciplined trial and error. We're going to kind of up the ante a little bit. This is reverse power rule. This is reverse trig. So you decide if you want to pause. Probably a good idea to pause and try it out on your own. And upcoming is my explanation. I know I need an x to the 4th power because this derivative has to end up being an x to the 3rd. So here's the question. 4 times what coefficient is going to leave me with the 8/3? So some people can do that in their head, some people have a problem. So a lot of times I go off to the side of the paper and I say 4 times what coefficient leaves me with 8/3? And then I have this little algebra problem. I solve for question mark, and I get 8/12, which to most humans is 2/3. Now if I'm doubtful of that, I simply stop, I wipe my brain clean, and I say 4 times 2/3 is 8/3, x to the third power. It works. All right, and then for this next one, you would think you would just do plus cosine of x. And then of course our plus c, don't forget that, we'll more on that later. But be careful, the derivative of cosine is negative sign. That's a positive sign, so I need the negative there. All right, let's keep on keeping on. This one's going to be a little bit surprising to you. The 1 over x, that's simply natural log. And a lot of times in calculus, the antiderivative will put an absolute value around the natural log of x, because remember, only positive inputs can go into natural log. So the derivative of natural log of x is 1 over x. Then this looks like it's product rule in reverse, but it's not, because if you remember your trig functions, the derivative of secant is secant tangent. And as always, stop after you do your antiderivative, literally wipe your brain clean by wiping your hand across your forehead, and take that derivative and see if you end up back there. Let's see if we have another. We do. It's a doozy. All right, so we have to swim back upstream. Now look at this. This ended up being an antiderivative of natural log of x. So the gut instinct is we would do natural log of x squared for the antiderivative of 1 over x squared. That turns out to be false, because if I took the derivative of natural log of x squared, if I really thought that was my derivative, oh, gotta reposition. If I really thought that was the antiderivative, I would take its derivative and I would get 1 over x squared times a ninja of 2x, which ends up being 2 over x. That means trouble. Natural log of x squared cannot be the antiderivative of that, even though natural log of x was the antiderivative of that. Here's the rule. If your exponent in a denominator is a 1, that's probably going to be a natural log antiderivative. If it's not a 1, then it's reverse power rule. So I view this as x to the negative 2 instead of 1 over x squared. And then I can do reverse power rule. Be careful, because in the land of negatives, your brain confuses you. Check this out. If I take the derivative, negative 1 times negative 1 is positive 1. X. Oop, hold on. Okay, sorry, I'm back. Unexpected problem there. So what I was saying is, if I took this derivative, negative 1 times negative 1 is positive 1. X to the, I have to lower the exponent by 1, so that lowers it to negative 2. So this would be a derivative of 1x to the negative 2, which is that. So now over here, I would view this as minus 6x to the negative 3. It can't be a natural log antiderivative, because that is a exponent that's not 1. So let's see, I have to go x to the negative 2, because its derivative has to lower that exponent by 1. And I'll need a positive 3 there. And then finally, for this one, secant of x squared is kind of 4 secant squared x. Remember that the derivative of tangent is secant squared. And we have one pretty nasty antiderivative. Okay, so we now know how to find the antiderivatives, which is a lot of just intelligent trial and error, reverse thinking of your derivative rules. But every time I did one of these, I had this little plus c, and we just kind of ignored it. But we can't ignore it, and I'll show you why on this next part. Okay, we're going to be finding what that C is. Instead of writing plus C, we need a value. It's going to be a pretty easy thing, basic algebra step. So we're going to start off with this derivative, but now we're given a little information. It says the original function f that we're finding at x equals 3, y equals 11. So we could call this 3 comma 11. And let's do the antiderivative first. Let's see, I would need an x to the third power, and then I would need, what would I need? I'd need a 2/3 there. 3 times 2/3 gives me 2x to the second, good, minus 4x plus c. That's what our antiderivatives were before, but now that we have this extra information, an x value and a y value, we can figure out the c. So remember, in algebra, they might say this is a y equals equation or an f of x equals. So here I go, I just plug in my 11, my 3, and I notice that c is the only thing remaining. I can solve for c. So, yay algebra. 2/3, and this is a 27, so that's an 18 minus 12 plus c. And if I solve for c, that's a 6. C equals 5. So that means my real f of x is that. Instead of writing the plus c, I can write the plus 5. So finding c is just a little extra add-on that basically involves algebra. All right, let's do this final problem. One more finding c. All right, we have a cosine of x plus 2. We want to swim upstream like a salmon and find its antiderivative. So I really should have labeled this as f prime of x. And they give us some information. They say function f, which we're trying to find, travels through pi over 2 comma 8. All right, well, let's go with the antiderivative first. Sine of x is the antiderivative. I should give a symbol. We're doing function f. Sine of x plus 2x plus c. I would take a moment, take the derivative. Derivative of sine is cosine. Derivative of 2x is 2. Life is good. Now I have an x value and a y value. Through the miracle of algebra, c is the only thing remaining. So I can go ahead and solve for c. Sine of pi over 2, thank you unit circle. Sine of pi over 2 is 1. Then this is pi. If I now move the 1 over to the other side, and then the pi over to the other side, why would you ever move pi over to the other side? Keep it on your side. I've got my c. So that means the combination of this initial antiderivative and my good work finding c my plus c is 7 minus pi. Ta-da! Okay, this was a long video, but now we know how to do antiderivatives and we know how to solve for c. My advice is, no matter what, after you do your antiderivative, take its derivative and make sure you end up back where your antiderivative started you. That's the only way to know if you're truly correct, and when you do that, you can end up making adjustments if you were wrong. See ya!